Imagine a locked box. This box holds your secrets. We call this box a cipher. In the digital world, ciphers protect our data. They scramble information, making it unreadable to prying eyes. This is the essence of cryptography. Block ciphers are like special puzzle boxes. They take information in blocks. Think of these blocks as puzzle pieces. The cipher scrambles these pieces using a secret key. Only someone with the right key can put the puzzle back together. These ciphers are essential in our digital age. They secure online transactions, protect passwords, and ensure privacy. Without them, our online world would be like a house with no locks, vulnerable to anyone who wants to peek inside. In the world of cryptography, there are two main types of encryption, symmetric and asymmetric. Think of them as two different ways to unlock our digital puzzle boxes. Symmetric encryption uses one key for both locking and unlocking. It's like having a single key for your front door. Both you and the person you share the key with can open the door. Asymmetric encryption, however, uses two keys, a public key and a private key. The public key is like your mailbox address. Anyone can use it to send you a message. But only you, with your private key, can open and read those messages. Each approach has its strengths. Symmetric encryption is faster and more efficient. Asymmetric encryption offers greater security, especially for key exchange. Both play vital roles in keeping our digital lives secure. Imagine you're sending a secret message, but each word is encrypted separately. This is the basic idea behind electronic codebook, ECB mode. It's the most straightforward way to use a block cipher. ECB works by taking each block of plaintext, encrypting it with the key, and producing a corresponding block of ciphertext. It's simple and efficient. However, ECB has a weakness. If the same plaintext block is encrypted multiple times, it will always result in the same ciphertext block. This can create patterns, making the encryption vulnerable to attack. Think of it like using the same word over and over again in a code. It becomes easier to crack. Section 4 CBC chaining blocks for stronger security. To strengthen security, cryptographers developed Cipher Block Chaining, or CBC. Imagine each block of plaintext being chained to the previous one before encryption. This chain adds an extra layer of complexity. In CBC, the first plaintext block is combined with a random block of data called an initialization vector, or IV. This ensures that even if the same plaintext is encrypted multiple times, the ciphertext will be different. This chaining effect makes CBC more secure than ECB. It hides patterns and strengthens the encryption. However, it also means that if one block is corrupted during transmission, the error can cascade and affect the decryption of subsequent blocks. Section 5. OFB turning block ciphers into stream ciphers. Output feedback, or OFB mode, offers a different approach to encryption. Imagine a stream of random bits being generated from the key. This stream is then combined with the plaintext to create the ciphertext. In OFB, the block cipher is used to generate a key stream, which is independent of both the plaintext and the ciphertext. This key stream is then XORed with the plaintext to produce the ciphertext. This mode has the advantage of being error-resistant. If a bit error occurs during transmission, it only affects the corresponding bit in the plaintext, not the entire block. OFB is often used in situations where transmission errors are likely, such as satellite communications. Section 6. CTR counting on secure communication. Counter mode, or CTR, shares similarities with OFB but uses a slightly different approach to generate the key stream. Imagine a counter that increments with each block of plaintext. This counter value is combined with the key and encrypted to produce a unique key stream block. In CTR, the block cipher encrypts a counter value that is incremented for each block. This encrypted counter value is then XORed with the plaintext to produce the ciphertext. Like OFB, CTR is also error-resistant and efficient for parallel processing. It's commonly used in high-speed applications such as network encryption.